to learn how to make your robots do this, then you're going to want to watch this video. In this video, I'll show you the concepts involved in making an FLL robot follow a line, and I'll even show you the code to do this. If you don't understand variable blocks and how to create MyBlocks with inputs, then you're going to want to watch the 2 previous videos that cover these topics. In this video, I'll cover simple zigzag line followers and then move on to describe proportional line followers. Lines on FLL mats are almost always 1-inch wide black lines with white borders around them, with the notable exception of the green lines in Senior Solutions. Also, lines on FLL mats rarely make sharp bends or are thinner than an inch. The line follower algorithm I'll present will be well suited for following the types of lines encountered in FLL challenges. My team found it beneficial to make a test course with a large loop in order to develop and test line follower algorithms. This test course was drawn on a 4x8 foot piece of paper. In order to make your robot follow a line, you are going to have to use a light sensor. A Mindstorm's color sensor can be made to function as a light sensor by using it in light sensor mode. The NXT light sensor consists of an LED and a light detector. Light from the LED reflects off the mat and its intensity is measured by the light detector. A black part of the mat will reflect less light than a white part, and this will allow your software to determine whether it's over a black part of the mat, a white part of the mat, or somewhere in between. To keep unwanted ambient light from influencing your light sensor, you should make it point straight down, have it fairly close to the mat, and build a shield around it with Legos if possible. My team and I determined that having the sensor a few millimeters off the mat works well for line following. The size of the circular LED beam shining on the mat is a fairly good estimate of what area the detector is looking at, so keep that LED beam smaller than the line you are following. Having a light sensor close to the mat makes it difficult to go over obstacles with your robot, so you'll have to get creative to figure out how to make a robot that can both follow a line and go over obstacles if necessary. I don't have access to a Mindstorm's EV3 set, so I'm not sure about the details of an EV3 color sensor. For a traditional NXT set, it is preferable to use the light sensor module rather than the color sensor operating in light sensor mode. The primary reason for preferring the light sensor for line following is that the light sensor provides measurements with much finer resolution in comparison to the color sensor. For example, a quick test on our robot revealed that the NXT light sensor raw value output differed by 180 when over a white and black part of the mat. In comparison, the NXT color sensor only differed by 20. Thus, the light sensor provides about 9 times more resolution than the color sensor. This increased sensitivity would allow the robot to follow a line more precisely. As an analogy, if you were making a thermostat, would you rather have a temperature sensor that could only tell you the temperature to the nearest 9 degrees, or a temperature sensor that could tell you the temperature to the nearest degree? Based on my research, I'm pretty sure that the EV3 can use old NXT light sensors. It would be very helpful if some kind viewer could leave a comment indicating whether the EV3 can use the old NXT light sensors without any degradation in performance. I'd also be interested in knowing how much of a difference there is between the value returned when the new EV3 color sensor is over a white and black part of the mat. This could help decide whether an old NXT light sensor would be preferable to an EV3 color sensor. Another reason why the NXT light sensor is preferred is that it can be calibrated, whereas the NXT color sensor cannot. Please see our video on the Amazing TubBot at about 3 minutes in to see a description of how to calibrate an NXT's light sensor. After calibration, the light sensor will return a value of 0 when over the darkest part of the mat, usually a black line, and a value of 100 when over the lightest part of the mat, usually a patch of white surrounding the black line. The line following algorithm we will present assumes that the light sensor is calibrated and will therefore provide values between 0 and 100. If you need to use a color sensor instead of the light sensor we're recommending, then you'll have to use math blocks to scale the output of your color sensor to provide values between 0 and 100 before using these values in our algorithm. This won't actually improve the resolution of the color sensor, but it should work with our line follower. Again, if a kind viewer with an EV3 kit could leave a comment regarding whether an EV3 color sensor in light sensor mode can be calibrated, that would be greatly appreciated. For line following, the light sensor should be positioned on your robot out in front of the drive wheels so that the sensor can look ahead at what's coming in the future and have a bit of time to respond to the changes. Steering the robot to follow the line is accomplished by independently controlling the power of the left and right motors. Power is varied to each motor in order to cause the motors to steer in such a way as to keep the light sensor following the edge of the line. This process is referred to as differential steering. The first time I thought about line following, I imagined an algorithm which attempts to provide power to the drive wheels in such a way as to keep the sensor seeing as much black as possible. The problem with this simplistic solution is that when the sensor starts seeing more white, the robot wouldn't know which way to turn in order to see black again. The line could have veered off to the right or left, and the robot software wouldn't be sure which direction to steer the robot in order to see black again. In this simplistic approach, the robot would have to guess in which way to turn, and if it guessed wrong, it might completely lose track of the line. Therefore, line following is best accomplished by following either the left edge or right edge of the line, instead of the center. Here's an example of a simple algorithm that can follow the right edge of a line. This algorithm works by alternately shutting down one and then the other of the two motors, which causes a zigzag motion. When the light sensor sees too much white, the left motor is stopped and the right motor is powered, causing the robot to pivot to the left, towards the line. When the light sensor sees too much black, the right motor is stopped and the left motor is powered, causing the robot to pivot to the right, away from the line. Here's an example of my robot running the simple line-following algorithm that follows the right edge of the line. When the light sensor sees too much white, the left motor is stopped and the right motor is run at power, so that the robot will turn inwards towards the line. When the light sensor sees too much black, the left motor is turned on and run at power, and the right motor is stopped, so that the robot will turn away from the line. Here's an example of line follower in action. Here's an example of a simple algorithm that can follow the left edge of a line. The right edge algorithm was altered by switching which motor block is set to 0. When the light sensor sees too much white, the right motor is stopped and the left motor is powered, causing the robot to pivot to the right, towards the line. When the light sensor sees too much black, the left motor is stopped and the right motor is powered, causing the robot to pivot to the left, away from the line. Here's an example of my robot running the simple left edge line following algorithm. So as you can see, when the light sensor is hovering over too much white, the left motor is turned on and the right one is turned off so that the robot will turn and pivot towards the line. And then when the light sensor sees too much black, the right motor is turned on and the left motor is stopped so that the robot will turn away from the line. Here's an example of the simple left edge line follower in action. This simple algorithm causes the robot to zigzag left and right. While this algorithm is able to follow a line, there are many things about this algorithm that are not optimal for an FLL robot. Time is the most precious resource in an FLL tournament, and this algorithm wastes a lot of time since the robot always has one wheel stopped. An algorithm that keeps both motors moving forward would result in faster line following. Of course, instead of looping forever, this algorithm could be modified to follow the line for a specified time, which would allow rough control over how far the robot would follow the line. The biggest problem with using this zigzag algorithm in an FLL mission is that after the robot follows the line for a specified distance, a major problem emerges. When the robot stops following the line and moves on to the next part of the mission, there is no way to guarantee which direction your robot will be pointing. Not knowing which way your robot is pointing before starting its next move may make it nearly impossible to make reliable and repeatable missions. For use in FLL, a good line-following algorithm would allow the robot to drive a specified distance at a reasonable speed and without it wiggling so that it would point in a consistent direction after its movement was completed. The proportional line follower algorithm can meet these requirements fairly well and isn't too hard to understand. Some teams use something called the PID algorithm, which is similar but has two more constants called Ki and Kd in addition to Kp. Tuning, which is finding suitable values for these constants, is quite complicated. Jay Slucka wrote a very good article called A PID Controller for LEGO Mindstorm's Robots, which is available online. However, our team found that the proportional line follower algorithm had good enough performance for our needs. The basic principle behind the proportional line follower algorithm is fairly easy to explain. The goal of the algorithm is to try and keep the value read from the light sensor at 50, which is halfway between black, which is 0, and white, which is 100. Another way of saying this is the circle of light emitted from the LED should be centered above the edge between black and white. In a proportional line follower, both motors move forward at equal speed when the sensor value is 50. If the light sensor is seeing just a bit too much white, say a value of 55, Then the proportional algorithm will make a small correction to one of the motors in order to try and make the light sensor see more black. If the light sensor is seeing a lot of white, say a value of 85, then the proportional algorithm will make a large correction to one of its motors in order to try and make the light sensor see more black. The correction that the algorithm makes is proportional to the magnitude of the error, which is why it is called the proportional line follower algorithm. Here's an example of my robot running the proportional line follower algorithm, which is set to follow the left edge of the line. So again, when the line follower sees too much white, the left motor is run at a faster speed and the right motor is run at a slower speed in order to turn the robot towards the line. When the line follower sees too much black, the left motor is slowed down and the right motor is set to a higher speed in order to turn the robot away from the line. Notice how when I gradually move the robot from the white area to the black area, how the motor speeds change. Here's an example of the proportional line follower in action. Notice how it's wiggling a lot less than the simple line follower algorithm. Before I start the description of the proportional line follower algorithm, let's establish some conventions about our robot. First, let's assume that our robot's right motor is wired to port B of the NXT brick and that our robot's left motor is wired to port C. Second, let's assume we have a robot with an NXT light sensor connected to port 3. Also, the light sensor should be located a few centimeters in front of the axes of the two drive wheels. Additionally, the sensor should be a few millimeters off the mat. The algorithm I'll present is based on these assumptions. Here's a block diagram of a proportional line follower. The user will specify a nominal motor power, a distance to follow the line, and a value called Kp. The line follower is an example of a feedback control loop. The light sensor measures the intensity of the light reflected off of the mat. This intensity is compared to the ideal of 50, and after some basic math, an error term is calculated. Using the computed error term, the line follower then computes the correction. The power to one of the motors will be reduced by subtracting the correction. If everything works as intended, the correction applied to the motor will steer the robot towards the black line if it is seeing too much white, or will steer the robot away from the line if the sensor is seeing too much black. The line follower I'm presenting will run both motors at the speed specified by the user if the error is 0. If the error is non-zero, then one of the motors will be decreased while keeping the other motor's powers at the user's specified speed. Thus, our line follower block will always have at least one of the motors running at the user's specified power level, which makes smooth, fluid movement possible. An alternative proportional algorithm could be used that simultaneously increases power to one motor and decreases power to the other motor in proportion to the error. My team experimented with both algorithms. We found that on our robot, the algorithm that decreases only one motor power at a time made our robot perform more smoothly at higher speeds. You may want to try both algorithms on your robot, but for the sake of brevity, I'm only going to present the algorithm that decreases one motor power at a time. The feedback loop starts at the sensor. The light sensor is read and will return a value we'll call LS, which is between 0 and 100. The ideal value is assumed to be midway between these two values, or 50, which would place the sensor immediately above the edge of a line. The next step is to compute the error term, which uses the equation 50 minus LS divided by 50. If LS was at an ideal value of 50, the error would evaluate to 0, which makes sense. If LS was at 100, indicating it was seeing the brightest possible white, then by plugging 100 in for LS, we can see that the error would evaluate to -1. If LS was 0, indicating that it was seeing the darkest possible black, the error would evaluate to +1. From the two extreme cases, we can see that the error will range from -1 to +1. If the sensor is seeing too much white, error would be negative. If the sensor is seeing too much black, error would be positive. The sign of the error is used to decide which of the two motors needs to be adjusted in order to better center the light sensor over the edge of the line. The magnitude of the error will control how much to correct the motors. If the error is small, then the correction should be small. If the error is large, then the correction should be large. Thus, the correction is proportional to the error, which is why this is referred to as a proportional line follower. The next block in the loop takes the computed error and turns it into a correction that will be applied to one of the motors. This is accomplished by multiplying the error by the user-specified power and a user-specified variable called Kp. Kp is called the proportionality constant. The normal value for Kp is 1. Changing Kp to be bigger than 1, 2.0 for example, will scale up the correction, which will make the corrections to the motor power more drastic. This might be necessary if you are following a line that has sharp bends or even right angle turns. Changing Kp to a value less than 1, say 0.5, will make the correction to the motor smaller, which has the potential to make the robot wiggle less when following the lines. Changing Kp to a number outside the range of about 0.5 to 2.0 might result in a robot that cannot follow a line, but it's nice to have control over how much your robot will wiggle when following the line. If you set Kp too low, the robot won't be able to follow curved lines. If you set Kp too high, the robot may overcorrect and even lose a straight line. Now let's address why power comes into the formula to compute correction. Power will be a MyBlock input that specifies the nominal power that the motor blocks inside the loop should be run at. You can set the power to anything from 0 to 100. All of my recent robots use the motorcycle wheels. In my experience, with these wheels, if you set the power too high, the robot will not be able to follow a line, no matter what. 80 is about the highest power I've gotten a line follower to work. When using high powers, expect your robot to zigzag. It takes the NXT motors some time to change speeds. They can't correct instantly, so there is a limit to how smoothly your line follower can behave at high power levels. Powers of 40 and below usually are necessary for smooth line following. The lower the power you use, the smoother your line follower will behave. But precious time will be wasted too. Let's get back to the line follower algorithm, and let me explain why multiplying the error by power is necessary. Don't forget, the range of the error is between -1 and +1. In the case when Kp is 1, multiplying the error by power will result in a correction between negative power and positive power. Thus, when Kp is 1, the largest possible correction will have the effect of zeroing the power to one of the motors, since power minus power is 0. Therefore, whether line following with a user-specified power of 20 or 40, the correction should depend on that user-specified power, which makes sense. Let's consider the case when the robot will be following the right edge of the line. The sign of the computed correction will determine which of the two motors needs to be corrected. If the correction is positive, then this means the light sensor is seeing too much black, and the program will go up here, slow down the right motor while running the left at power, which will cause the robot to turn to the right, which will be away from the black line. If the correction is negative, then this means that the light sensor is seeing too much white, and the program will go down here and slow down the left motor, which will cause the robot to turn to the left, which will be towards the black line. This corrective steering accomplishes the feedback within the feedback loop. When Kp is set to 1 or less, the magnitude of the correction will always be smaller than the user-specified motor power. However, if Kp is set greater than 1, then it is possible that the correction will evaluate as larger than the user-specified power. In such an instance, the result of subtracting the correction from the motor power would result in a negative number. Through experience, I have seen that setting an NXT motor's power to a negative number causes undesired results. A switch block was added to both the top and bottom branch, and these are used to prevent the motor power to either motor from being set negative when the correction is too large. Whenever the correction is larger than the user-specified power, that motor's power is set to 0 instead of letting it go negative. Without this, the line follower would not behave itself when Kp was set greater than 1. After correcting the power to one of the motors, we then check to see if the robot has finished traveling the user-specified distance using rotation sensors for motors B and C. NXTG provides rotation sensor blocks that let you determine the number of degrees each of the motors has rotated. Each time through the loop, the rotation sensor for each of the two drive motors are checked. The left and right rotation sensor values are averaged, and then a check is done to see if the robot has traveled the user-specified distance. If it hasn't gone far enough yet, it loops back to the beginning, and the entire process starts again by reading a new value of the light sensor. If the robot has gone far enough, then the loop is exited and both motors are halted just before the end of the MyBlock. Here's a description of the line follower algorithm in pseudocode. Please pause the video if you would like to study the details of the algorithm. Here's the NXTG code for implementing the line follower pre-MyBlock. This pre-MyBlock can be used to generate the actual MyBlock by first highlighting all of the blocks, starting with this KP variable, and going all the way to the end of the file. It would take me too long to do this right now, but once you've selected all of the blocks, you then can select Make a New MyBlock from the Edit menu. Before doing this, make sure you have your pre-MyBlock backed up, and after doing this, make sure to exit the pre-MyBlock file without saving the changes. The MyBlock will be created in your blocks/MyBlocks directory, and you should be able to see it under the MyBlocks tab. For more information on making and using MyBlocks with inputs, please refer to my previous video on MyBlocks, which contains a wealth of information that isn't presented in this video. As can be seen here, the MyBlock generated from this pre-MyBlock will have 4 inputs: KP, power, distance, and left edge. The version of these variables with the in prefix exist only in the pre-MyBlock and are used to provide test values to the MyBlock inputs. The KP input is a number variable that scales the line follower's response to an error measured at the light sensor. The normal range of KP is from roughly 0.5 to 2.0. You'll want to experiment to find the best value of KP for each situation in which you are using the line follower. The power input is a number variable which defines the nominal speed that the line follower motors will operate at. In theory, power can range from 0 to 100, but again, you'll want to experiment to find the best power to run your robot at for a situation. If you want your robot to follow the line without any wiggles, so that its final position is guaranteed, lower powers are preferable. The distance input is a number variable that specifies the distance in millimeters that you want your robot to follow the line. This distance will be converted to a number of degrees to run your motor, which depends on the wheel radius of your robot. Please refer to our MyBlock tutorials for details. The left edge input is a logical variable input that tells the robot which edge of the line to follow. Setting left edge to true will cause the line follower to follow the left edge of the line. Setting left edge to false will cause the line follower to follow the right side of the line. In this section of the MyBlock, several variables are initialized. C180 over pi is used in the distance calculation and is set to 57.296. Threshold is set to 50, which is the midpoint between the black and white light calibrated light sensor values. Motor direction is a logical variable that is used to define whether your robot's motors are mounted forward or backwards. Setting it to true means the motor block actually moves your robot forward when asked to. Setting motor direction to false means the motor block actually moves your robot backwards when asked to move forward. Wheel radius is a number variable which should be initialized to your robot's wheel radius in millimeters. This group of 6 blocks is used to calculate the variable degrees to go, which defines the number of degrees to run the motors in order to go the distance in millimeters requested by the distance input. Degrees to go is calculated outside of the loop in order to save time within the loop. These blocks implement the formula shown on the screen. Consult our MyBlock video for more information. These next 4 blocks simply calculate the product of the KP input and power input. This calculation is done outside of the loop in order to keep the number of calculations within the loop to a minimum. A tight loop will run faster and should perform better when the robot is requested to move at higher power. These next 2 blocks reset the rotation sensors for the 2 motors connected to the drive wheels. Rotation sensors are used within the loop to determine how many degrees each motor has rotated. This is the start of the loop. The loop will repeat until the robot has traveled the requested distance. The light sensor is red, which returns a value between 0 and 100. The error calculation begins here, by first subtracting the sensor reading from 50 and then dividing the result by 50. The output of this divide block is the error, which ranges from -1 to 1. The error is then multiplied by the kp times power variable, which was calculated outside of the loop. The result is stored in the correction variable, which defines how much to adjust the power to one of the motors. The ABS correction variable is set to the absolute value of the correction. The absolute value function changes the sign of the negative numbers, while leaving the sign unchanged for the positive numbers. The next set of blocks checks to see if the power input is greater than the absolute value of the correction. If it is, then power low is defined by subtracting the ABS correction from power. Power low will be the reduced power level that will be used to drive the power to the appropriate motor. If the ABS correction is greater than power, it will go down here and set power low to 0. Subtracting ABS correction from power would result in a negative number. The motor block expects positive numbers, so a negative number would cause it to malfunction. To prevent a negative motor power, power low is set to 0, which halts the motor block. The value of left edge selects either the top or bottom branch of the switch block. When true, the algorithm computes motor powers that will fall the left edge of a line. When false, the algorithm computes motor powers that will fall the right edge of a line. Let's trace through the case when left edge is false. Correction is checked to determine if it is positive or negative. For such a comparison, the B input port of the comparison block should be set to 0. Unfortunately, there is a bug in the NXTG compiler that sometimes generates incorrect code when comparing something to 0. We have found a way to work around this intermittent malfunction. The trick is to use a value of 0.01 in the comparison block instead of 0. This effectively does what is intended and will compile correctly as well. I recommend that you use a value of 0.01 instead of 0 so you don't get frustrated with this compiler error. Okay, let's get back to the description. Remember, we're tracing through the case when the line follower is tracing the right side of the line. When correction is greater than 0, this indicates that the sensor is seeing too much black, so the algorithm must slow down the right motor in order to turn the robot towards the patch of white to the right of the line. In order to accomplish this right turn, notice how power right is assigned the reduced value of power low, and power left is assigned the value of power. If correction is negative, the sensor is seeing too much white, so the lower part of the switch block will execute making the robot turn left in order to steer the sensor into seeing more black. If the left edge input were true, then this top part of the outer switch block would run. You'll notice that values for power left and power right will be opposite what they were in the case when the right edge was being followed. After setting power right and power left, these values are applied to the right and left motor blocks, respectively. Remember, we had assumed that the motor block B is connected to the right motor and the motor block C is connected to the left motor. Since each motor block requires a unique power, 2 motor blocks are used to control the robot's motor instead of a single MoveBlock. The direction port on both motor blocks is controlled by the motor direction variable, which was defined outside of the loop. Remember, line following will only work if the robot is moving forward, with the light sensor out in front. If your robot starts moving in the wrong direction, then initialize motor direction with the opposite value. Let's look at how to set the other inputs to the motor block. When using a motor block inside a feedback loop like this, the duration must be set to unlimited. In other words, we're not asking the robot to move a specific number of degrees. We're just telling it to keep moving at the power that was computed earlier in the loop. This final group of blocks in the loop will be used to determine if the robot has traveled far enough, and if it has, the loop will be exited. Rotation sensor B is read and written to a variable called rot_b. Rotation sensor C is read and written to a variable called rot_c. Since both rotation sensors were reset just prior to the start of the loop, the rotation sensors will provide how many degrees each motor has rotated during the line following process. The rotation sensor values could be either positive or negative depending if your motors are installed forward or backwards. These next blocks take the average of the 2 rotation sensor values by adding them and dividing them by 2. The absolute value here is necessary because depending on how you installed your motors on your robot, the average could be either positive or negative. Finally, the average number of degrees the robot has moved is compared to the number of degrees that was computed earlier. If the robot has traveled far enough, the loop will be exited, otherwise execution will continue at the first block in the loop. Once the loop has been exited, the port B and port C motors are stopped by using the brake. After that, the light sensor LED is turned off. That completes my presentation of how to make a line follower MyBlock. I'd like to mention how to make this MyBlock function on any robot you design. 2 different robots your team has built could have different sized wheels or have the motors mounted in opposite directions. So how can you make this MyBlock work without any changes for the robot your team designs? The answer is by removing the blocks that initialize the variables wheel radius and motor direction. In NXTG, all variables are global, so you can initialize these variables outside of the MyBlock, and the NXTG compiler will use the values inside the line follower MyBlock. Our team has found having a MyBlock for each robot that simply defines the wheel radius and motor direction variables is the way to go. Early in the FLL season, when we have few robots we are playing around with, it is really handy to have a single MyBlock that will work with any robot without any changes. The performance of a line follower depends on several physical characteristics of your robot. The distance from your light sensor to the axes of your drive wheels, the distance between your robot's drive wheels, and the radius of your robot's tires. Once you make a line follower MyBlock, you can experiment by changing these things to see if you can improve the line following by making it go faster or straighter. If you find anything wrong or have helpful suggestions or questions, please leave a comment below. I want to emphasize that this line follower provides just the beginning of what you can do. Once you understand the concepts presented in this video, you can improve this MyBlock substantially. How about adding a second light sensor that will stop your robot if it detects a perpendicular crossing line? How about when you are first following the line to have a larger KP and lower power so that the robot can have time to get oriented to the line? How about doing a series of pivots to get the light sensor directly over the line before starting line following? Perhaps you can follow the line at high power at first, and then change the power to a very low value after the robot has traveled 90% of the desired distance. This could ensure a quick trip, while also making the robot carefully orient itself with the line at the end. The possibilities are endless. Watch my video on TubBot for additional ideas. If you like this video, please take the time to comment, rate it, and share it with other FLL teams. Have a good FLL season!